All right, so welcome to another lovely day here of statistics. Um, Hopefully, everybody had a good weekend. Today's plan is to pretty much pick up where we left off. We talked about the normal distribution last time and how it's kind of a big deal. You'll see why. Today, we're going to talk about the central limit theorem, which basically um, it tells us how reliable samples are, basically, um, in terms of telling us about the actual population. And then after we talk about the central limit theorem, we'll start looking into what we call confidence intervals, which are exactly what they sound like. They are intervals that we create that then basically tell us how confident we are about our population values, population means, proportions, and so on. All right, so that's my plan. But as always, I want to start by going over any homework questions or any questions you guys have. And I know earlier Carson hit me up to look at normal distribution problem number 4. Can you tell me which section from the normal distribution we're looking at?
Not the concepts, the
Okay, just the
problems.
problem sets. Okay, cool. I can definitely do that.
It's a specific question. I don't know if it is different on yours, but mine is it's problem C on number
Okay.
4.
All right. I will go ahead and write that down. We'll see how similar mine is. And then, so Ali, you said, can we go over one from each section? Um, each section meaning every section we've done up until this point, every section on normal distributions. Can you give me a little more information what you mean? Okay, the ones that are due today. All right, well, I will take a look at what all those are and see what we got. So, not the concepts. Okay, put that on my list. Anything else? Okay, so I'm going to go ahead and share my screen in a second, but I figure we might as well get this out of the way. We got the Star Wars T-shirt of the day. This is one of my uh, more favorite ones because it's got a little crossover to The Simpsons and Futurama. You got Bender trying to drink at the cantina where it says "No droids." Yeah, there you go. Anyway, so let's go ahead and hit up the homework here. So let me share my screen and we'll go take a peek at those. Okay, so let's start here with normal distribution. Go look at the question that Carson asked about, number 4. All right. So hopefully this looks kind of similar to what you had, Carson. Is it?
No, mine's different.
Okay. What's yours?
My problem C, it's asking, they're considering offering a discount of the patron who spend the least time at the hot springs. What is the longest amount of time a patron can spend at the hot springs?
Okay.
That's the specific.
Well, let me, we'll try a different question. Okay, hold on. So, all right, I tell you what I'm going to do. I'm going to stop sharing here for a second, and I'm going to find that another way. So let's just go ahead and entertain yourselves for a moment. Now, what I'm going to do is actually find Carson's specific homework problem because I can do that. And then I just need to get to a point where nobody can see all the different grades and everything. So give me just 1 second here. All right, so let me share this again. All right, so hopefully everybody can see this one. So this is Carson's specific question, but yours might be similar or not, but let's look so we can address his question for C. So we got the amount of time that people spend at Grover Hot Springs is normally distributed with a mean of 71 minutes and a standard deviation of 15 minutes. So again, remember mean is average, right? It's a dead center. And then the standard deviation tells us what the spread is like. And with the normal distribution, we do have, we know exactly, well, we know roughly what percent are between the different standard deviations. When you go one standard deviation on each side, do you guys remember what percent of the information is within that region, within that range? From the empirical rule. All right, thanks, Willie. It is 65%. So 65% are within one standard deviation. What about two standard deviations? How much do we catch then? Good, thanks, Willie. It's 95%. So basically what this one's telling us is that if you were to go 30 minutes on each side, so between 41 minutes and 101 minutes, 95% of the people that come to Grover Hot Springs spend some time in between those. All right, so that's what standard deviation is telling us, is just the variability, the spread. Okay, anyway, so now suppose one person at the hot springs is randomly chosen. All right, so we just are in there, we close our eyes and we just point at somebody and say, all right, you, we want to know this about you, right? This is how much time they spent. All right, so first of all, before we get to C, let's kind of see what happens here. So for the first part, what is the distribution of X? Well, it is normal, and we always go with our mean and our standard deviation. Okay, so then find the probability that a randomly selected person stays longer than 75 minutes. So that one, we can use the normal CDF, right? Normal CDF, going from 75 to infinity, basically, and ends up giving us about 40%. Okay, so let's look at part C. So part C says the Park Service is considering offering a discount for the 8% of their patrons who spend the least time at the hot springs. What is the longest amount of time a patron can spend at the hot springs and still receive the discount? All right, so what's going on here is we're going backwards. We're going backwards from part B, basically. Right? You look at part B. Part B was asking us to figure out a probability given an amount of time. Now we want to go backwards. We want to get an amount of time given a probability, right? So this time we're saying, well, they want the discount for the 8% who spend the least amount of time. So for the lowest 8%. Okay, well, let me draw a picture. I'm a huge fan of pictures. I think they definitely help us see what's going on. All right, so think about a normal distribution. It looks something like this. All right, we got our good old bell shape. For this one in particular, we know that the mean was 71 minutes. Now, what we're interested in is what value down here is going to make it so that this is 8%. Okay, because we're trying to find what time, what amount of time makes it so that if you're below that time, you're therefore, you're in the lowest 8%. Okay, so before we actually do that, are you okay with the idea here? And specifically you, Carson, are you seeing what they're asking us to do?
Yeah.
Okay. All right. Now, to do this, though, the command that we need to use for our calculator, we need to use the inverse norm. Because remember, inverse brings us backwards. So this is the inverse normal. So it's going to do the normal distribution, but backwards. Okay. So let me pull up my calculator emulator here for you, my TI-84. So hopefully everybody can see my TI-84 now. And so we need to find the inverse norm. It's going to be under distribution. So that's that second function here on vars, distribution. And you'll see the third one down the list is inverse norm, INV norm, inverse norm. So we're going to go there. So I'll click on 3. And notice what it asks. It first asks, what area do we want? All right, now for the inverse norm on the TI-84, this area we give is the area that's to the left of our value. So for us, this is going to be 8%. We're trying to find the bottom 8%. So I'm going to put 0.08. All right, but then it asks our mean. Well, for this problem, our mean was 71. And then it asks for our standard deviation, which I think, was it 15? Am I remembering that correctly? I hope. All right, so I hit enter again. So this is what we're going to do. We're going to do the inverse norm of 0.08 because we want 8%. And our mean and our standard deviation are 71 and 15. So I hit enter. And it spits out this number. So 49.9, roughly 50, right? That's the amount of time at which, if you were there for less than this, you're in the bottom 8%. Okay, so 92% of people spend more than this much time at the hot springs. So to get to this one, we need to do an inverse norm. All right, so let me go back to my picture because I want to ask you guys another question here. All right, so we just found that value, right? That was 49.9. But what if I wanted to do this? What if I wanted to give a, special prize to people who are there the longest? And maybe I want to know what value up here is going to make it so that that if you're above that, you're in the top 5%. So let's think about what we'd have to put into the inverse norm, all right? Because if you think about the inverse norm, remember what we did. We put in the area, and then the mean, and then the standard deviation. So for this one, if we're going to try to find the top 5%, the mean and the standard deviation are still going to be the same. But what would I put in for this area? What would I put in for that area to find this number right here?
0.05.
All right, so 0.05. What do you guys think? Let's start with that. Is that 5%? If I could see your faces, hopefully. Yeah, so your head should all be bobbing. Yeah, that's definitely 5%, right? So 0.05. Well, I'll tell you what, let's try it. let's go back to the calculator, and we're going to run the exact same thing. So we'll go distribution, number 3 for inverse norm. But this time, let's put in 0.05. Keep the same mu and the same sigma. So we'll just hit enter a couple times, do its thing, and we get 46.327. Okay, so let's go back to the picture. So think about where 46.27 or whatever, think about where that is. That's actually down here. So when we went with 0.05, we didn't actually get the number we wanted. All right, now I didn't catch who that was that gave me 0.05 as an answer.
Yeah.
Okay, thanks, Kira. So you weren't wrong about 0.05 being 5%, but unfortunately it didn't give us what we wanted. What did it actually give us? What is that 46.27 telling us?
The lower 5%?
Yeah, it's the lower 5%. There are 5% that are below that number. We are looking for 5% above a number. So anytime you use inverse norm, whatever number you put in there for your area, for your percentage, it's giving you the percentage that's below your number, not above. Okay, so I guess the same question then is, how can we adjust this so that whatever number I put in here actually does give me the value of interest? Does anybody see what we can do?
Would you use the inverse of 0.05?
Not the inverse, but
Okay.
you're on the right track. How about this? Remember what we're looking at is what's the area below that? That's what inverse norm tells us. So what's the area
Willie has it.
below that number? Yeah, Willie, thanks for putting that in. What we're going to actually put in here is 0.95. Because if we have 5%, we want to know where 5% is above. That means 95% is going to be below. So when you do your inverse norm, make sure you're always thinking area below. And if you are actually interested in area above, do 1 minus that, right? The 0.95, that's the 1 minus 0.05. So that would be the trick to find that value. So let's go take a look at it again. We'll go back to the TI 89 or 84 here. Let's do distribution, inverse norm. This time, let's do 0.95, but same mean, same standard deviation. And you notice the number that we get now is like 95.67. And so if we were to go back and look at where that is on our graph, 95.67, well, that's definitely a reasonable number for up here, right? It's very many minutes above 71. So that's one way that you can actually get that value if you're looking for something above. But I'm going to show you another trick for that too. Instead, like let's say we didn't want to actually do this inverse norm, we had just done the 5%. I want you to check this out. Look at what the difference is between 71 and 49.9. Oh, not 49.9, sorry, 46.27. Okay, so you take 71 minus 46.27. We'll put in our decimals. And you get 24.73. Well, check this out. Take 71 and add to it. Not 29, 24. And put a couple decimals there. We get 95.73. Now, I know that that's not quite 95.67, but to be honest, the 46.27, I didn't remember exactly what those numbers were, but at least it's ballpark. And the reason we can do this is because of the symmetry of the normal distribution. It looks exactly the same on either side. So if we're going to go a certain distance to go to the lower 5%, you'd go the same distance the other way to get to the upper 5%. So that's another approach, although I'm just a huge fan of diving straight in with the inverse norm. All right, so feeling better about that one, Carson?
Yeah.
Yeah.
Pretty much covered it.
Okay, cool. So anytime you're asked for a percentage, that's where we need to go to the inverse. So the inverse norm. We're going to be doing quite a bit of that later today, the second half of today. All right. So I think that was the only specific question somebody asked about. And then Allie, you asked us to look at one from each section. I think because I moved chapter 7 to next week, I think only chapter 6 is due this week. Is that correct? And I'm looking to you guys because I don't actually do the homework, so I am not as familiar with when they're due as you guys.
Correct.
So I think that's kind of where we are, but I'll tell you what, Allie, let's save some of those from chapter 7 for after we talk about the central limit theorem. So what we'll do, we'll talk about the central limit theorem. I'll show you some examples, and then I'll come back into the homework and we'll try a couple. We'll kind of jump around into those different sections and try a few. All right. So basically, I still owe you. All right. But we'll do that in a little bit. All right. So are we good to learn a little bit about the central limit theorem and what it means and what it says?
Commence the learning.
All right, let's do this. All right, so I'm going to go ahead and switch screens, and I will be back with you guys in just a second. All right, so clearly I'm still working on dimensions and everything because now all of a sudden I've got my really big head really close. You're not used to. Well, we'll get this figured out. But anyway, so let's talk about this thing called the central limit theorem and what it means and what it tells us. Okay, so first of all, from here on out, I'm not going to write out central limit theorem. I'm going to write CLT. Okay, so if I write CLT, that just means I'm doing the central limit theorem. Now, central limit theorem, there are actually two forms to this. And it depends what we're looking at and what we're measuring, which form we use. Okay. The first one is the central limit theorem for sample means. So just use the words, and I'll tell you what this is. So it's means of samples. So we're taking a sample, right? So let's say we're looking at, heights of adult males. And we go out and we grab a sample of 25 adult males. We measure their heights. We get the average of it, of that. That's that sample mean. So that sample has a mean height. All right. So that's what we're talking about when we're talking about sample means. The other form is for sample sums. So it too is what it sounds like. It's we're going to take and add up all those numbers. So let's say we're doing the same thing. We're going out, we're going to sample 25 adult males, get their heights. This time, instead of averaging them, getting a mean, this time we're going to sum them all up. And so we would get the total height of these 25 adult males. Okay, but it's always for the samples. We're not talking about the mean of the population. No, we're talking about the sample mean. We're not talking about the sum of the results for the population. It's for the sample. All right, so this is the two different forms. All right, well, what does the central limit theorem say? All right, well, for both of these forms, what's kind of nice is that if n is large, okay, so n, remember what n is in general when we're talking about statistics. N is the size of our sample, right? So if n is large, put here, big sample. So if n is large, then what we know is that the distribution of the sample means, and I'm going to put in parentheses, or sums, okay, depending upon which one we're doing. But regardless, if n is large, the distribution of these sample means or sums will follow a normal distribution. So normal distribution, you remember about that. We were just talking about it. But basically what this is saying is that I'm going to go out, sample my 25 adult males, and I take their average height. Okay, then I go and I select another sample of 25 adult males to get their average height. And then another sample and another sample and another sample. If I look at the averages from all those different samples, they're going to start following the normal distribution. And the same thing happens if we look at the sums. All right, so basically it's just we grab a sample and look at their average height. Grab another sample, grab another sample, grab another sample. You would start plotting those numbers and the frequencies, you'd start seeing a distribution that looks bell-shaped. Okay, so this is the first non-normal distribution that leads to normal distribution. It's going to be kind of a common theme. Now, here's what's kind of interesting. I think this is actually the power of the central limit theorem, is that the sample means, while they follow the normal distribution, the population itself can follow any distribution. All right, so I'm going to actually write that down here because this is kind of big. So the population may not be normal. In fact, it could be uniform. It could be exponential. It could be geometric. It could be any of the distributions that we've seen or the distributions that we haven't seen. All right. So it's kind of a big deal that regardless what your population is, how it works, if you look at samples, those samples, if you sample large enough size, we'll talk a little bit about large enough in a minute, but it's going to start following a normal distribution. Okay, well, if they are going to follow normal distributions, we should probably be able to describe them like we did other normal distributions and calculate things like z-scores and all that. So let's look first at sample means. We'll get back to the sample sums in a little bit, but let's start with the idea for sample means. All right. Okay, so first of all, just for some notation, right? So X, this was the random variable for the population, right? And again, I'm going to put in parentheses, any distribution, doesn't matter. All right, and let's say that it's got a mean of mu. I'm going to put sub X, and it's got a standard deviation. We'll call it sigma sub X. All right, so these are the mean and standard deviation for the population. All right, so you're used to those symbols, but I just want to make sure that we've got this clear. All right, now for the sample means then, we're going to create a new random variable. And that new random variable is going to be X bar. All right, and so what this is the sample means. In general, when you put a bar over, that means average or mean. Okay, so it's going to be our sample mean. So we know that if n is big enough, we have a large enough sample, that this is going to follow a normal distribution. So the question is, what are the mean and standard deviation of the sample of, or the distribution of sample means? Okay, well, this is actually kind of nice. It turns out that the mean is still the same. Okay, so if we go out and we sample 25 adult males and get their average height, that distribution is going to be such that the average height from the samples is the same as the average height of the original distribution population. Okay, so it follows the same mean. Now, the standard deviation is a little bit different. It's actually smaller than the population standard deviation. And if you think about it, it kind of makes sense that it should be. Because remember what standard deviation is the spread. If I go and I just test one individual, I go grab one random adult male, the likelihood that I get someone who's much taller than average or much shorter than average, while not huge, it's definitely possible, right? I can randomly end up choosing someone that plays basketball, right, professionally. If I randomly pick LeBron James, he's going to be a bit taller than average American, right, or average adult male. Same thing for someone shorter, right? I could go and I could grab Peter Dinklage, the guy from Game of Thrones, right? And he's going to be shorter by, than the average male, adult male, right? So that can happen. Now think about what's going to occur now. I'm going to go and I'm going to grab 25 people, 25 adult males, and look at their average height. The likelihood that their average height is going to be way different than the average height of an adult male is smaller. Because think about what would have to happen. I'd have to go and get my group of 25 to be all really tall people, or they'd all have to be really short people. And the likelihood isn't that that's going to happen, right? Can I still pick LeBron James in my collection? Sure. But he's going to be one of 25. The other 24 are going to be regular old normal people, most likely. That's going to bring the average back closer to what the true average is for the population. All right, so it should make sense that it's going to be smaller. So we're going to divide by a number to make it smaller. Now, the other thing that should make sense is that if I go and I sample a larger group, it's way less likely for that larger group to have big fluctuation. So if n gets bigger, this number should get smaller. And in fact, it does. And what we find is that the standard deviation of the sample means distribution is actually the standard deviation of the population divided by the square root of the sample size. Okay, now where that square root comes from, I'm not going into that. We're not going to go there. But mathematically, it can be shown that that's how the sample standard, or the standard deviation of sample means is affected. All right, so notice that you start getting a big group. This goes down a lot, right? So if I go and I sample 25 people, square root of 25 is 5. I've cut that standard deviation down by a fifth. So think about that one that we were just looking at for Carson, just because I remember that number was 15, right? That standard deviation was 15. Well, if we look at the sample means of people spending time at Grover Hot Springs, and we were to sample 25, the square root of 25 is 5. So that would bring that standard deviation down from 15 to 3. From 15 to 3, that's a huge shrink. What if I went and I sampled 100 people? Well, the square root of 100 is 10. Now I'm going to reduce it by a factor of 10. So in that same example, if we went and we looked at samples of 100 people that went to Grover Hot Spring, instead of getting a standard deviation of 15 minutes, it's down to 1.5. So it's a huge reduction with our greater n. But it should make sense that the more we sample, the less variation we're going to get. Hence why our standard deviation for the sample means goes down. All right, so there is a name for this guy right here, the standard deviation of the sample means. And so I want to give you this name so that when you see it, you know what we're talking about. This is called the standard error in the mean. All right, so if you ever see something that says, hey, calculate the standard error in the mean, This is, calculate that. All right, so let me show you how this works. Let's actually do a problem here using the central limit theorem regarding sample means. So you can kind of see what you're going to have to do, like on homeworks and stuff. All right, so let's say, for example, that the average age of registered cars in the US is 84, no, that's good, 96 months. Okay, so 96 months is 8 years. All right, so on average, the age of a registered car in the US is 8 years old. So there are some that are older, like mine. My car's 17 years old. I love it. Got a 2004 Toyota Corolla. It's great gas mileage. All right, so you get cars like mine. They're definitely older. There are also ones that are younger than that, like my wife's car. It's a 2009. Right? Oh no, not 2009, 2019. So it's definitely younger, right? But on average, we're going to go 8 months. Let's say we also know the standard deviation. And the standard deviation is 16 months. All right, now, I didn't tell you how the ages of cars, of registered cars, is distributed. We don't know if it's uniform, if it's normal, or whatever, because that's not going to be relevant when it comes to the central limit. All right, but here's what I want to do. Let's say that we go and we sample 36 cars. So we're just going to go out and randomly collect 36 cars and sample them. And so here's the first question, is what's the probability that the mean age of these cars is between 90 and 100 months? So that's going to be the first question that we answer. So what's the probability that the mean age of the cars in our sample is between 90 and 100? All right, so if we were just going to be looking at one car, and we want to know what's the probability that the one car we find has an age between 90 and 100 months, you would just use your good old normal CDF, right? You do normal CDF with your mean of 96 and the standard deviation of 16. And you go lower bound 90, upper bound 100, right? So you know exactly what you do if it was normally distributed. Well, this time though, we're looking at a sample of 36 cars, but we're going to actually approach it exactly the same way. We are still going to use a normal distribution. We just have to change, we have to adjust the values of the mean and the standard deviation. All right, so here's what we're going to do. We need We know X bar, right, follows a normal distribution. So let's put in what the numbers are going to be. So we need the same mean as the mean of the population, which was the 96. So we're at 96 here. But then we need the standard error, and we need this new standard deviation. So we're going to take the original standard deviation, which was 16, and we're going to divide it by the square root of the number in our sample. So our sample is 36 cars. All right, well, let me reduce that a little bit because we can take the square root of 36, that's 6. 16, 6 reduces down to 8/3. So we'll just go ahead and leave it like that, right? All right, so this is the normal distribution that we're doing. So let's see what we're going to do to answer this question. All right, we want the probability that the mean age of this sample is between 90 and 100. Okay, so we're going to do a normal CDF from 90 to 100 with these mean and standard deviation. All right, well, I went ahead and I did this a little bit earlier. And what you end up what I ended up calculating was 0.92, I think it was 10, rounded to 4 decimal places. Right? Or in this case, 92.1%. So there's a over 92% chance that if you were to go out and sample 36 cars, that their average age would be somewhere between 90 and 100 months. So very likely, right? It's very likely that this would be the case. All right, now we're gonna have a little bit of fun. Instead, let's just alter this to, what if it was just one car? What's the percent likelihood that its average age would be between 90 and 100? Okay, well, for that, we'd still do a normal CDF. Still going to be between 90 and 100. But this time, the mean and the standard deviation are going to be 96 and 16 instead of 96 and 8/3. Do you guys see why it's 16 and not 8/3?
Because the square root of 1 is 1.
I'm sorry, can you say that again?
16 divided by the square root of 1 is 16.
Okay, so if you want to use that formula, right, the square root of n, in this case, we've got just one sample, be 16. So that's a great way to think about it if you want to use that formula. Or we can just go with, well, if we're just doing the one sample, it's standard, it's the normal distribution, and that's its standard deviation, right? So assuming a normal distribution, which if you don't know otherwise is a good assumption, would just lead to, well, yeah, use that same sample standard deviation, or sorry, population standard deviation. All right, so it's going to look a little bit different. But here's where it gets really kind of cool. If you actually do that calculation, check this out. So we're going to go from 90 to 100. And I'm typing in my calculator right now. I've got a mean of 96 and a standard deviation of 16. And what we end up with is 0.24458. Which is good, 0.2446. All right, so that's 24.46%. Okay, so think about what this means. I go out and I just randomly choose a single car. I've only got about a 25% chance, a 1 in 4 chance, that its age is between 90 and 100 months. But if instead I go out and I look at 36 cars, calculate its average age or their average age, it reduces it. It reduces the standard deviation so much that the likelihood that that occurs is now 92%. So this really shows you how there can be a lot of variation in individuals. But when we group them up and look at them as a sample, the variation goes down. And that's the key to the central limit theorem. So if we want to go out and try to figure out something about the population, the bigger the sample, the better. Because the larger the sample, the more likely it is to follow or more likely it is that we're going to be close to the mean of the population, the actual value of the population that we're interested in. The variation, the variability kind of gets erased. All right, so kind of get the feel for this, I hope. It really just is, the only difference is now we got to divide by that square root of n on a standard deviation because we're getting way less variability. All right, well, that was the first one, right? Remember I told you that there were actually 2 forms. This is the first one, the central limit theorem for sample means. But let's look at the one for sample sums. But before I go there, any questions on this? Kind of see how it played out. All right, hearing none and seeing none. Let's look at the second form, the central limit theorem. Okay, so this was the one for sample sums. All right, so now this time what we're doing, again, we've got our x, right? And this is the random variable for the population. Now what we're going to do is we're going to create a new one called sigma x. So hopefully you remember this capital sigma that's telling us to add. Right, so that's going to be sigma x. Well, this is also going to follow a normal distribution. Just like with the sample means, the sample sums are also going to follow a normal distribution. So, so this time we're adding them all up, right? We're taking the sample and we're adding all the ages. We're taking the sample, we're adding all the heights, we're adding all the whatever it happens to be. All right, so then the question is, what do the mean and standard deviation look like for this one? Now, unlike the sample means, both of these have different mean and standard deviation in the population, but they're both related to. Okay, the mean is going to be n times the population mean. And if you think about this one, it should make total sense. If what I'm doing is adding them all up, the first one has an average of mu, the second one has an average of mu, third one has an average of mu. Mu plus mu plus mu plus just add. That's multiplication. One for each in our sample. So we're going to take mu and we're going to multiply it by n because we're taking a sum. Okay, so that mean is going to be considerably larger depending upon the size of our population. All right. So then what about the standard deviation? Well, the standard deviation is also related to n. But it's going to be the square root of n times the standard deviation before we divided by the square root of n, right? Actually divided by the square root of n. This time we're going to multiply by the square root of n. Okay, so that one might feel a little bit weird, but again, it kind of makes sense if you look at it mathematically. Think about what we did here. We took the mean and multiplied by n. So the mean of the samples, which happen to be the same as the mean of the population. Well, imagine that you were to take the sample mean, remember the sample mean standard deviation was this, multiply it by n. If you take n divided by the square root of n, you get the square root of n. So mathematically, it makes sense that we're multiplying by the square root of n now. Don't worry about that. That was just a little bit of the math behind it. All right, well, we basically get to do the same thing that we just did, except now we're looking at totals. We're looking at total amounts and calculating probability. All right, so here's an example for this one. Let's say that we're researching the amount of sugar in our favorite soda. All right, so you've got your favorite high quality root beer. You're looking at the amount of sugar that's in it. All right, so let's say that we know that for a certain soda, the mean amount of sugar is 39.01 grams. And let's put this per can. 31.01 grams with standard deviation of 0.5. All right, so on average, 39.01 grams, and then standard deviation is 0.5. All right, so what we're going to do is let's say that we sample 100 cans. All right, so we head down to the local grocery store, go to Rayleigh's, grab a couple of cases. And we go over Safeway, grab a couple of cases. And we just go wherever, get a whole bunch of different cans, but we have 100 cans of the same soap. All right, so here's my question. Well, we'll do a few questions, but let's start with this one. So question number 1 is going to be, I guess we'll call it A. And what is the probability that the total amount of sugar is more than 3,910 grams? Now, what we should expect, if we're going to have on average 39.01 grams, we should expect something like 3,901. We'll multiply that by 100. So this isn't a lot more than that, but let's see what that probability gives us. All right, so what command are we going to use? What are we going to tell our calculator to do here? Then I'll yell it all at once. All right, I'm assuming there are still people here who just don't know what's going on.
I'm here.
Okay, so, all right, so Bruno, thanks for saying you're unsure. I appreciate that. Okay, so we know that it's a normal distribution. So we're going to want to use one of the normals. So do we want to do, think about, we have 3 choices. We've got normal PDF, normal CDF, and inverse norm. Right? So let's think about, of those 3, do we want PDF, CDF, or inverse norm? So let's think about what all the different ones do. So PDF gives you the value at that point. So it's basically giving you the graph. CDF adds them up over different values. And inverse norm gives us a number for a specific percentage or specific probability. Okay, well, we can eliminate the inverse norm right away because we already know we don't have a probability. We're looking for a probability. So you can get rid of inverse norm. So then PDF or CDF, well, it needs to be CDF because we're looking for more than 3,910. So we're looking for an interval from 3,910 on up. All right, so this one we're going to do a normal CDF. All right, so let's think about what the different values are that we're going to need. So the lower bound is going to be 3910. The upper bound, I want it to be basically infinity. And remember our trick. We're going to type in 1E99. As soon as I get this set up, we'll go down. I'll go to the computer and we'll pull up the calculator so you can see the keystrokes sequence. So those are our values, but then we also need our mean and our standard deviation. Okay, so then our mean value is going to be 100 times 39.01. So that'll be 3901. Again, where that came from was doing 100 times 39.01. And then the standard deviation that we're going to put in is actually going to be 5. Now where that came from is the square root of 100 times 0.5. Right, so again, I'm using this formula right here, square root of n times sigma. All right, so I'm going to go ahead and share from my computer so you can see the keystrokes and how we do this. All right, so we got our TI-84 up. So again, we're going to go to distribution. So second vars gets our distribution. We're going to do normal CDF, number 2. All right, our lower bound was 3,910. Our upper bound, we're going to do 1, and then the E, you can see it right here, the E, comma, so we do second E, 99, so that's 1 followed by 99 zeros, so really, really big number. All right, so then we need our mean. Well, this is the mean of the sums of our sample. So 3901. And then we need the standard deviation for the sums. So it's that square root of 100 times 0.5, which is, all right, so we hit enter. So notice that that's going to do what we wanted it to do. We hit enter one more time. And we get a pretty small number. Right? We find that this probability was 0.0359. So that's under 4%. There's an under 4% likelihood that the total amount of sugar is going to be more than 3,910 grams. All right, I don't know if you quite understand how kind of huge this is. Because think about what the mean was. The mean that we expected was around 3,901. Right? That would be what 100 cans on average should have. The number that we were looking for wasn't off by much. 9 grams. Right? 9 grams of sugar over 100 cans. That's a very little bit. But we just saw that for us to be off by that much, it's highly unlikely, only 4% of the time. If I were to do this 100 times, only around 4 of them am I going to find a number bigger than 3,910. So when we start getting large numbers, and this is why this happens, because of a large number of cans, almost 100, 100 cans. When you get to large numbers, your variability shrinks. Your variability shrinks. it's way less likely for these things to occur. Like, okay, let's extend it. I mean, we went to 3,910. Let's just go a little bit further. So here's question B. Same 100 cans, right? So we're still looking at these 100 cans. But here's the next one I want to look at. What's the probability that the sum is between, and we're not going to go very far on either side. We were at 3901. Let's go up and down 10. Now let's go a little bit further. Let's go between 3,875 and 3,925. So roughly 25 grams on either side. Right? So 100 cans. What's the probability that with those 100 cans, we're going to be within 25 grams of each side? All right, well, let's go to the calculator and let's put in our values again. All right, so we're going to do the same command. We're going to do distribution, normal CDF. Okay, we need to change our lower and upper bounds. Our lower bound is now 3875. Our upper bound is 3925. And we're going to use the same mean and the same standard deviation. All right, so does that look right? 3875, 3925, 39015, hit enter. All right, so look at that number, 0.999991058. That's awfully close to 1. So remember what a probability of 1 means? Probability of 1 means that it's gonna happen. Well, that's pretty much what this just said. If you were to go out and look at 100 cans like this, you're virtually guaranteed that you're going to get a total amount of sugar between 3,875 grams and 3,925. Doesn't seem like it's a very big spread. And yet we're already pretty much guaranteed that we're within. Right? But this is the power of large numbers. If your samples are big, it's very likely that what you want to occur or what you think will occur will occur. All right, let's take a real quick break. I'm going to go ahead and pause this. And let's come back in, say, 10 minutes, the top of the hour. I've got 4:50 right now. So let's come back at 5. And we'll look at a couple of examples from the homework, right, for Allie. And then we'll move on to talking about confidence intervals. So see you guys in 10 minutes. Okay, so we're back. Now that we've talked a little bit about the central limit theorem, let's see how we can apply it to homework questions. So I'm going to go ahead and share my screen and we'll go look at some homework questions from these sets just so you can kind of see how this plays out. So what I've got up here is one of the ones from the central limit theorem about means. And it's just question number 4, just grab this one at random, but let's see how this relates to what we talked about. So it says the average amount of money spent for lunch per person in the college cafeteria is $7.08. And the standard deviation is $2.38. Okay, so we've got a population mean and a population standard deviation. All right, so suppose that 17 randomly selected lunch patrons are observed. Assume the distribution of money spent is normal and round all answers to 4 decimal places where possible. Okay, so they actually did tell us a lot about the distribution. We've got a mean, we've got a standard deviation, and we're even told that it is normal. We're going to assume that the distribution is normal, which is probably what we would do anyway. It kind of makes sense to think that it's not going to be uniform. You're not just as likely to spend $20 on lunch as you are to spend $5 on lunch, right? So it kind of makes sense that it would be normally distributed. All right, but we're going to go and we're going to sample 17 people. So let's start with part A. So part A says, what is the distribution of X? All right, so it says X is normal distribution. What are the mean and standard deviation we're going to put in here? And this is where you guys play along. I'm not doing this for you. I'm doing this with you, okay? So what are we going to put in those first 2 boxes? All right, so Allie just put 7.08 and 2.38. And that is exactly right. Those are going to be our values because those were the values for the random variable itself, right? This has nothing to do with the means or anything. That's just the sample means. This is just the mean and standard deviation of the population, of the distribution itself. Okay, good. So that'll be our first row here. All right, so now the second one says, what is the distribution of X bar? So remember X bar, that means the average of the X's, so the means. So this is our sample means. All right, so what's the mean of our sample mean distribution? All right, cool. A bunch of you are throwing it in there. It's 7.08. It's the same mean as for the regular distribution. And this is definitely where we get some inception stuff going, right? Dreams within dreams, means within means. So it's really important to remember what we're talking about. Are we talking about sample means versus population means, even though in this case, they end up being the same. All right. And so then what do we do to get the standard deviation? Good. Allie just put in the chat box 7.08 divided by the square root of 17. And it's going to be the square root of 17 because, well, we're looking at a sample of size 17. All right. Do you guys know, will it let me do this? Maybe if I said square root. Nope. Okay. Thanks. Carolina just gave me that. So 0.5772 rounded to 4 decimal places. All right. Thank you for that. I don't know where I put my calculator. Frantically looking around for it. Oh, I got it. All right. So it's a different distribution, but it's a distribution of sample means. All right. So then for a single randomly selected lunch patron, find the probability that this patron's lunch cost is between these 2 amounts. Uh-oh, do we have some question on what that value is? Willie, yes, it is 2.38 divided by the square root of 17. And Allie said you're getting a different number. Let me see. I actually agree with what Carolina gave us here, 0.5772. I get 0.5772, 3478, 7586. So rounded to 4 spots, I think we're good. All right, so Allie, hopefully you figured out what you did. You just put never mind. But. All right, so now let's go to part C. So part C, for a single randomly selected lunch patron, find the probability that this patron's lunch cost is between 7.8242 and 8.5628. All right, so what command? Give me that first. What command are we going to use? Okay, good. CDF, normal CDF. Which mean and which standard deviation? Well, don't bother which mean because it's the same mean, but which are the two standard deviations? The one from part A or from part B? All right, so Willie and Bruno, thanks for throwing in some stuff. So you guys, you're going to use the one from part B. Well, I hate to break it to you, but that's not the one we want to use. We actually want to use the one from part A. Okay, so this is when we all go, well, shit, how do you know? How do I know that I actually want to use the standard deviation of 2.38 instead of 0.5772? What in the wording here tells me that? Yeah, good, Willie. I'm looking at a single randomly selected lunch patron. I'm not looking at the sample here. I'm looking at just one, right? I'm just going in and I'm pulling one person and saying, hey, how much money did you spend? Because it's just one person, we're using the distribution for just the random variable itself, not the mean of the sample. Okay, so when I go and I do my CDF, my normal CDF, I'm going to put the lower bound of 7.8242, the upper bound of 8.5628. My mean will be 7.08 because it's the mean regardless. But for the standard deviation, I'm going to put 2.38. All right, so my calculator just did that for me. And so I'm going to go ahead and put it in here. And I got 0.1106. So with your technology, go ahead and do it. Hopefully you get the same number. But that's what you should get when you're using the first distribution. And we're using the first distribution because of a single randomly selected patron. All right, so let's go to part D. So for part D, for the group of 17 patrons, ooh, key word, right? Group of 17 patrons, find the probability that the average lunch cost is between the same two numbers. All right, well, it's still going to be a CDF because we're still looking at a bound. But now, instead of using the 2.38 as our standard deviation, now we're going to use the 0.5772. Excuse me. And that's because now we're looking at the sample, right? So we're going to look at this. I'm sorry, was that question? No? Okay, so now we're using the distribution from part B. And what I get when I ran this, 0.0935. Okay, so it's less likely that this group has their average lunch cost in the same interval, right? And that's because if you look at this interval, 782 to 856, that's straying away from the mean. So those are already kind of unlikely numbers. So they're more unlikely once we go to the group. All right, so then what about this? For part D, is the assumption that the distribution is normal necessary? When we were looking at the group of 17 patrons, was that assumption necessary? All right, so Willie says no. What do the rest of you guys think? All right, well, nobody else has given me anything. I'm going to go with Willie's. Let's see. All right, so we'll go ahead and submit our question. Uh-oh. So Bruno says, then it's yes. Well, if it's not no, then it must be yes. All right. So, okay. So Ali, yeah, hold on one second. I'll show you what to do there. I think they actually have a typo here, because for part D is the assumption that normal is necessary. I actually agree. No, it isn't, because we're looking at the distribution of the sample means, and we already know that that tends to follow normal distribution. Although actually maybe because of the size of the sample is not very large, might be why they're saying that. For sure, we did have to assume that the distribution of the original was normal in order to do the single person. But let me back up here, because Ali just said, how would you set up D in the calculator? So let me do this. Let me share my whiteboard so I can write down exactly what you're going to put in. Or no, not whiteboard. I'll show you the calculator. We'll actually do it. So Ali, what type of calculator do you have? Okay. So it should look a bit like mine, more or less, right? So what we're going to do, we're going to go into distribution. So you're going to do second, and then the vars to get your distribution. We're going to do the normal CDF. So press 2. Okay, so now we're going to put in our lower and upper bounds. So in terms of those amounts, the lower was 7.8242. That was our lower cost. And our upper cost was 8.5628. Okay, so that was the bounds. In terms of our mean was 7.08. And then for the standard deviation, so this one, we actually could type it in with the square root number in it. Or we can go for what we found when it was already rounded, 0.5722. I think that was our number. Nope, 5772. So this is what it should look like. All right, so I hit my enter. And I get that same number that I found using my calculator. All right. So does that help, Allie? Is that good? All right, awesome. Okay, well, let's do this. Let's go find a problem from the next set. And yes, I know I'm not done. And oh, it didn't give me the warning message. Doesn't it usually say, hey, are you sure you want to leave? So let's go find one from the sums formula or section so you can kind of see how this plays out as well. So we'll just choose one at random. All right, so suppose that the amount of time that students spend studying in the library in one sitting is normally distributed with mean 49 minutes and standard deviation 21 minutes. So a researcher observed 7 students who entered the library to study, ran around all answers to 4 decimal places where possible. Okay, so what is the distribution of X? So X is a normal distribution. So what are the mean and standard deviation here? All right, cool. That was a nice quick one there, Allie. This is for 49 and 21. Right, because we were told that the students, they were normally distributed with a mean of 49 and a standard deviation of 21. All right, so then what's the distribution for X bar? So how about we'll start here. What's the mean for this one? All right, so Allie again put in the chat box 49. Are you sure it's 49? No. Well, be sure. Yes, it is 49. And the reason it's 49 is X bar, that's our sample means, and our sample means have the same mean as our original distribution. So that one's still 49. And this one, the standard deviation, well, this is again sample means. So we're going to find it the same way we did the other one, which is to take that original population standard deviation and divide it by the square root of our sample size. So if we look back up here, it says a researcher observed 7 students. So we're going to take 21 and we're going to divide it by the square root of 7. All right, so what I get is 7.9373 if we round to 4 decimal places. So part A and B are the same as what we just did in that other homework one from the other section. Because X bars, that's our sample means. But now when we go to C, this is where it's a little bit different. In part C, this is what's the distribution of sum of X's. So what's the distribution of the sums? All right, so what's the mean going to be this time? All right, so Willie just put 343 in the chat box. How'd you get that? Why 343? Okay, good. It was 7 times 49. It's n, so the number in our sample, times what our mean is for the population. So 7 times 49. Cool. So that's going to be 343. And then for the standard deviation, this time, instead of taking 21 and dividing by square root of 7, we're going to take 21 and multiply by the square root of 37, which gives me 55.560708 if I go to 4 decimal places. All right, so again, that one came from the square root of 7 times 21. All right, so all three of these are following normal distributions, right? We're using the normal distribution for each one of them. A, we're using the normal distribution because they told us it was normally distributed. And then B and C, we're using the fact that this approaches the normal distribution as n gets bigger. All right, so now let's see if we can answer the other parts. So first, if one randomly selected student is timed, find the probability the student's time will be between 47 and 54 minutes. All right, keyword. What's the keyword in part D? Actually not and. The and is important to tell us that we're going between these, right? But the key in terms of what distribution we're going to use is 1. Because it's one randomly selected student, we're using the distribution for the variable itself. Okay, so this one's going to be using the mean of 49 and the standard deviation of 21. All right, so let's jump to the calculator just so you can see how everything's going to get put in here. All right, so again, go to distributions, normal CDF. Okay, lower bound is 47. The upper bound is 54 because we want times between 47 and 54 minutes. We had our mean was 49 and our standard deviation was 21. All right, so that was just for plain old X. So what we get is 0.1320. All right, so that's what I'm going to put into my box for the next one here. For one random student, the probability that they're between 47 and 54 minutes is 0.1320. So 13% of the time. All right, so then part E. For the 7 students, find the probability that their average time studying is between 47 and 54 minutes. All right, so which distribution are we using now? Which part, A, B, or C? So I'm not hearing or seeing anything. So maybe we're not sure. All right, thanks for the honesty, Ashton. I appreciate that. Not sure. Okay, well, here's what we're looking for. We're trying to find the probability that their average time is between these numbers. So which of these 3 shows average? Okay, good, Allie. It's part B. Remember, the symbol for average is the bar on top. So this right here, that's your average. That's your mean. So we're going to use part B. All right, so let's go back to the calculator. And let's do this again. So we're going to do distribution, normal. Our lower and upper bounds are still the same. Our mean was the same, but our standard deviation was different now. That standard deviation was 7.9373. And that was the one that was found when we divided by the square root of n. Okay, so if we do this, we end up with a much larger number of 0.3351. Okay, so let me go back over here. So 0.3351. So again, notice that these times are right around the mean. The mean was 49, and we're just very close to that. And notice now it's much more likely that the average studying time is in this interval around the mean, because we're looking at a larger group, right? A bigger group makes this more likely. Okay, but again, the key word there was average time. Think about the words again. One randomly selected student. The average time studying. Now let's look at F. F says, find the probability that the randomly selected 7 students will have a total study time more than 371 minutes. Okay, now this one's going to be the distribution from C. And how do I know that? What in the wording here tells me use C? Good, Allie, that's exactly it. It's total study time. Total. That means add stuff up. All right, so total study time tells me I'm looking at a sum of my x's. So that distribution is going to have a very different mean and standard deviation. All right, well, let's go use our calculator for that. Real quick before we jump over, let's just check what we're looking for. Probability that the total study time is more than 371. All right, well, that's still going to be a binomial or a normal CDF, because we are normally distributed, or at least we're assuming so. And we want a group of numbers, so normal CDF. So now our lower bound is going to be 371, because we want more than 371 minutes. And for the upper bound, since I want it to be pretty much infinite, I'm going to do 1 and then do the EE button and then 99. So it's as big as the calculator is going to ever think anyway. So 1E99. All right, well, I have to change my mean. Now the mean for the sum was 343. Oops. Went one too far here. Let's try that again. All right, and then my standard deviation, this was the one that we found by taking the square root of 7 times the original 21, which was 55.7. 5608. All right, so enter. We do its thing. And so we get 30% chance, 0.3071. All right. So hopefully you're seeing how you can tell the difference which one you use. And this really does highlight something that I mentioned before, like early on with stats, is that these are all word problems. And it's really important to read closely because the words tell you what to do. And for this one, it doesn't seem like they're very different, at least in the question they were asking or the structure. But those little differences, those key words, were sufficient enough for us to know what to do. Okay. So for part E and F, is the assumption of normal necessary? I'm going to say, yeah, since we're only looking at 7 students, that's not a very large group. But let's look at part H, because now part H is a little bit different. So it says the top 15% of the total study time for groups of 7 students will be given a sticker that says, "Great dedication." All right, how awesome would that be? Get the little sticker that you can, wear with pride that says "Great dedication." If you can't tell, I was being sarcastic. All right, but let's see if we can answer this. We want to find out what is the least amount of total study time that a group can study and still receive a sticker, meaning that they were in the top 15%. All right, so a couple of questions here. First, which of these 3 distributions are we going to use? Are we going to use A, B, or C?
C.
All right, so I just got C from a couple of you. And that's exactly right. And why? What's the wording in here that tells me you see? Good. Thanks, Ashton. Total time. Again, it's the total study time. So total tells me add them up. That's a sum. So I'm going to use the distribution from part C. Okay. So what command am I going to actually use though? PDF, CDF, or inverse? All right, so Ali just put inverse with a question mark in the chat box. You really should change that question mark to an exclamation. Inverse. We're going to use inverse. Why? Why are we going to use the inverse this time? Yeah, thanks, Bruno. All caps. Quit yelling at me. All right, so why is it that we're going to use the inverse norm? Good. Ali just put because of the top 15%. Remember, when we're looking for a percent or a number that corresponds to a percentage, that's where inverse norm comes in. Okay, so we're going to have to do an inverse norm for this guy. All right, so let's go to the calculator and start doing some calculations. All right, so we'll go to distribution, inverse norm, number 3. All right, so what are we going to put in for our area? So remember, the area has to do with the percentage. Okay, so I'm getting some 0.15s, and Bruno gives me an exclamation mark with it. Be careful, because that exclamation, that could mean factorials in math. So, but I appreciate your enthusiasm. So we're getting 0.15. All right. Hate to break it to you, but if we do 0.15, we're going to be wrong. So how do you feel about that exclamation now, Bruno? Okay, so why is it not 0.15? Why is 0.15 going to steer us wrong? I'll give you a hint. Think back to the one we were talking about earlier. Yeah, William said like that problem. Yeah, like that one problem that we were talking about when we wanted the top 5%. This one, again, we're looking for the top 15%. But inverse norm calculates the bottom. Yeah, so we got to subtract that from 1. So what we're going to actually use here is 0.85. Inverse norm gives us we give it the percentage below that number. So if we're looking for the top 15, they're above 85, the lower 85. So we're going to put in here 0.85 for our area. Okay, so again, if you're looking for the top, you have to remove that from 1. All right, well, there's our area. So let's go to our mean, 343, because that was the mean of our sum of x's. And then our standard deviation for our sum of x's was 55.5608. All right, so be careful with the inverse norm. Just because it says 15% doesn't mean you're putting in 0.15. If it's the bottom 15%, yep, put in 0.15. If it's the top 15%, got to subtract from 1. Whew. All right, so that's an enter. Let's see what number we get here. So let's see, 400.5851. All right, so let's go back to our homework problem here. Okay, so again, this says, what is the least total time that a group can study and still receive the sticker? Well, that's going to be the 400.5851. Basically, what we did, we found percentiles, right? This was the 85th percentile. And that's what inverse norm does, is it gets you the percentile. And percentile is always less than or equal. Okay, so for this problem, we see that there are actually 3 different possible distributions. There's the distribution just for the population itself. There's the distribution for the sample means, and there's a distribution for sample sums. All right, and they all, they're all normal, so they all behave the same way, but they have different means and standard deviations, which means they're going to have very different results when it comes to probabilities between different intervals. All right. So hopefully this was a good shove. And I want to say it was Allie who asked about these. If not, I'm going to give you credit for it, Allie. I wanted just to see some samples from these. So hopefully with these, you're going to be what I just did right now. You should be able to move forward with these homeworks and feel a little bit better about them. Okay, well, I see that we actually have 10 minutes left of class, and that's not enough time for me to really start getting into confidence intervals. I'm quite confident that I couldn't get very far. So what I'm going to do is we're going to go ahead and call it a day now. Let me stop sharing. But before we sign off, any other questions or things? Oh yeah, actually, let me just remind you. So there is going to be a quiz next time, a quiz on Thursday. And I'm going to make that quiz on chapter 6 for sure. That's normal distribution. Yeah, we'll just make it on chapter 6. Okay, so on Thursday, there's going to be a quiz on chapter 6. Like always, the quiz will be available starting at 3:30. And then you just need to get it uploaded by 4 o'clock. And at 4 o'clock, we'll start in here with class. And what we'll do is we'll talk about confidence intervals. I imagine that'll be pretty much everything we talk about on Thursday. I should also have the exams graded, at least that's my hope, have the exams graded by Thursday. So we'll probably go over those as well. All right. But that's everything from me. Any questions from you guys before I stop recording?
So aside from the normal distribution, will the central limit theorem show up on the quiz?
Not on this quiz, nope.
Oh, okay. Thank you.
Yeah. Central limit theorem will probably be on the quiz the following week. But no, for this one, it'll just be normal distribution. But good question. All right, well, with that, I will wish you guys a wonderful couple of days, and I'll see you all on Thursday.